Homework busy? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
Question 35 states that one proposed fusion reaction combines lithium and deuterium to give helium-4 in the following reaction. How many kilograms of lithium would be needed to supply the energy needs of one household for a year, estimated to be 3.8 times 10 to the 10 joules? Okay, so this question doesn't really tell us a lot. We know the total energy we want to be able to determine. So what we can do, if we can determine from the reaction above the energy per a singular reaction, I'll call N. Really, singular reaction means a single lithium atom. So from computing this, we know the energy per singular atom. We know we can find the relationship for mass of lithium, which is what we're trying to solve for ultimately. In kilograms, I think it says. Yes, kilograms. We can relate the mass to the number of atoms based on the relationship, mass of sample over molar mass times Avogadro's number. So we can replace this N with this relationship. And if we take the ratio total energy over energy per reaction, this will just equal number of reactions, which we can use that to rearrange the right-hand side of this equation to solve for mass. So that's my strategy for this question, is based on this equation shown here. So first thing we'll do is we'll solve for the energy per atom of lithium. So this reaction, E over N, like most of our equations so far, or situations so far for this type of question, it's simply the change in mass times C squared. Now we're just doing it per singular atom of lithium, so nothing changes in the calculation other than the relationship, including or making note that it is per singular atom. So I'm going to type this out. Actually, I'll write it out because it should be fairly short. So we take the absolute value of our products, our final products at 2 times the mass of helium-4, given as 4.003, minus the mass of deuterium, minus the mass of lithium, all with the units of U. We know 1 U is equivalent to 931.5 MeV per U per C squared multiplied by C squared, which results in a total value. U's cancel out, C squareds cancel out in terms of MeV. Again, this is, I'll say, per reaction. Don't forget that term there. We find this is 21.42 MeV per atom of lithium. Note that the final energy is given to us in joules, so we'll convert this into joules. Multiply this by 1.6 times 10 to the negative 13 joules per MeV. We can find that this energy in joules per atom, again, is 3.428. I'll leave myself a little more decimal places, just so I'm a little more accurate in my final answer, because we don't need to round intermittently. Times 10 to the negative 12 joules per atom. Cool. So now we have, if you look at our kind of our gold equation here, we have this term here. We're already given this one. So we can solve for the number of atoms. However, that's not as useful because we want to solve for total mass. So if we do a little bit of rearranging that equation, we can find that this energy over E over N, energy per reaction, is equal to mass over molar mass times Na. So looking at this equation, we know this term, we calculated this term. M is what we're solving for. Molar mass is always known, and Avogadro's number is always known. So we can simply solve for this value now. Rearranging this equation, we have mass equals our total energy, or the energy for the household, times molar mass divided by E over N times Avogadro's number. Just a little divider here, just so I'm not mixing up my terms. We can solve for the mass, so total energy, 3.8 times 10 to the 10 joules, 10 to the, not 10 to the, interesting, 10 to the 10 joules times the molar mass of lithium, which we found are used in the first place, 6.015 grams per mole. This whole term divided by E over N, which we calculated to be 3.428 times 10 to the negative 12 joules per atom, or N we'll say, and multiplying by Avogadro's number. Times 10 to the 23, we'll say atoms, or N, per mole, per goal. Yep, that would be nice. Per mole. Double checking our units real quick. Joules cancels out, number of atoms cancels out, 1 over moles cancels out, and we are left with grams. So plugging in these values into our calculator, we find that the number of grams is 0.111 G. But finally, we're asked for our final answer in kilograms based on the question. So it's simply be 1.1 times 10 to the negative 4 kilograms. And there you go.